In this video, we continue talking about sequences and finding their behavior as n goes to infinity. And I will continue with showing you how I expect you to solve these questions on the test. So again, we're going to talk about something that has been covered in Cal 1, and that's this very known limit, that the limit of sine of theta over theta as theta goes to 0 is the same as the limit of theta over sine of theta. Be careful, the limit only, right? And that's equal to 1. Okay, so we'll do a few examples involving this, easy examples involving this limit. So for example, if the sequence an is being given as n squared over 2n minus 1 times sine of 1 over n, okay? At the very start, we have infinity times 0, because as n goes to infinity, this one goes to infinity, right? And always goes to infinity when we talk about sequences, because it's a rational function where the order of the numerator is greater than the order of the denominator, times this whole thing here approaches to 0. Why? Because as n goes to infinity, 1 over n approaches to 0, and sine of 0 is 0. And infinity times 0, we know how to solve this using the L'Hopital's rule, but that's a little bit too much. So if I want to find the limit of an, that's going to be the limit of n squared over. Now I first tried to see, to simplify this expression right here, factor n, you get 2 minus 1 over n, and I don't do anything with 1 over n, with sine of 1 over n as n goes to infinity, which is equal to the limit as n goes to infinity. We cancel this and this, 1 over n goes to 0, so I get n over 2 sine of 1 over n. Okay? And now even if you just prepare this for to use the L'Hopital's rule, you'll see that you can stop right there. You don't have to continue. Here is again, I have infinity times sine of something that goes to 0. The whole function goes to 0, so I will say that this is sine of 1 over n over 1 over n. Okay? But now I have exactly this limit right here, sine of theta over theta as theta goes to 0, right? Because you don't have to write this down, but this boils down to, if we let theta is equal to 1 over n, okay, theta goes to 0 as n goes to infinity, right? If I just change the variable, I say instead of 1 over n, I get put theta. Then what happens to theta as n goes to infinity? Theta goes to 0, because 1 over n goes to 0. So this can be written, and I say you can drop this line, you don't have to. So theta goes to 0, sine of theta over theta, and I know that this limit is 1, so 1/2 times 1 is 1/2. Okay? So you can jump from here to here, just checking that sine of an angle that approaches to 0 divided by the same amount that goes to 0 with the same rate, that ratio will simply go to 1. Sorry, to be more precise, this limit goes to 1, and this 1/2 is from here. Okay? Now usually they give you this, they give you different versions of this. They give you different versions of this limit. Let's say an is equal to sine of e to power negative n over 2 times e to power negative n, okay, which is sine of 1 over e to power n over 2 times 1 over e to power n as n goes to infinity. This ratio approaches to 0, and this ratio also approaches to 0 with the same rate. So this limit, the limit of this ratio goes to 1. So I get 1/2 times 1 is 1/2. Okay, so be careful about sine of theta over theta as theta goes to 0, right? Let's say square root of n times sine of 1 over n. As n goes to infinity, this guy goes to infinity. This factor goes to 0, so this is sine of 1 over n over 1 over square root of n. Now what can we do? I can adjust this, just multiply by, divide by 1 over n, so that I will get that sine of theta over theta as theta goes to 0 limit that approaches to 1. But if I divide it by 1 over n, I have to multiply by 1 over n. So this limit approaches to 1 over n over 1 over square root of n, which is square root of n over n, which is 1 over square root of n, and that approaches to 0 as n goes to infinity. All right, you can cancel these. Okay, similarly, you can for example, the fourth problem, n times 1 minus cosine of 1 over n. Okay, so what do we have here? As n goes to infinity, this factor goes to infinity. This factor here, now, be careful, cosine as, 1 over n goes to 0, cosine of 0 is 1, so 1 minus 1 is 0. Again, I have infinity times 0. So what do you have here? Here you have 1 minus cosine of 1 over n over 1 over n. Now, one way to do this without the L'Hopital's rule is to multiply the numerator by its conjugate, okay? And then I'll have 1 minus cosine squared, which is going to get me to sine squared of 1 over n, okay? And then I can adjust to use that rule. But sometimes it's much easier just to use the L'Hopital's rule. It's faster, right? So, because this derivative here is 0, so I get negative times cosine, derivative of cosine is negative sine, so negative times negative sine of 1 over n times the derivative of 1 over n by the chain rule. And now look at this. I'm not evaluating this derivative. Why? Because I'm dividing by the same derivative by the L'Hopital's rule. I'm not going to bother evaluating that derivative, not that it's difficult, but so in order to, so here I have to write limit, right? Because I need to be precise with the notation. And then send n to infinity, this goes to 0. Sine of 0 is simply 0. Okay? Of course, don't get in the trap of, let's say, an is equal to 1 over n factorial times sine of n factorial, let's say. Okay? Be careful. Don't fall in the trap. Sine of theta over theta goes to 1 as long as theta goes to 0. In this case, n factorial, as n goes to infinity, n factorial goes to infinity, so I cannot apply this idea, okay? So then the question is, well, how am I going to solve this? Well, I have to use the squeeze theorem. No matter how big n is, sine of n factorial will always be bounded between -1 and 1. Okay? And then if I want to obtain an as an expression right here, bounded between these two terms, I need to divide both sides by n factorial. Because n factorial is positive, it's not going to affect these inequalities, so you get -1 over n factorial less or equal to sine of n factorial over n factorial less or equal to 1 over n factorial. This goes to 0 as n goes to infinity, this goes to 0 as n goes to infinity, which by the squeeze theorem implies that an, which is this expression in the middle, goes to 0 as n goes to infinity. Okay, so don't fall for that trap. Doesn't mean that whenever you see sine in your sequence, you will have to use sine of theta over theta.